Now, I'm not surprised. There's a lot of background
Yeah.
that's sort of implied here.
Okay. Yeah. Because in the 80s, I studied chaos. So when chaos first become popular in the 80s, when I was Shang-Chen's age, when I was 21 years old, and then I studied this pendulum, nonlinear pendulum, how they go from all kind of chaotic behavior. But then I lost track. Okay, so this is clearly different from what I knew before.
Yeah. Well, I mean, the point is that if you ignore, if you model the system by some, deterministic partial differential equation for the evolution of time, you find that there are many possible stationary states at late times. Because obviously, what we're interested in is this stationary state the system comes to, eventually reaches.
Mm-hmm.
And in the deterministic version of the PDE, there are a huge number of possible stationary states, usually a continuum of them. However, if you believe that you're modeling some experimental system in some reasonable way, then this should explain some experiments. But I mean, experimentally, it looks more as if you actually end up with essentially a unique stationary pattern.
So does this system have external drive or some kind of a energy consumption?
It's a driven out of equilibrium system.
So there is the energy input in the process, right?
Yeah, there's something that drives out of equilibrium.
Okay.
Sure.
Okay. So basically, this system does not obey the principle of detail balance, does it?
No.
It doesn't.
No.
Right.
Well, in general, no.
Okay. Uh-huh.
But even so.
Okay. Let me just give Shang-Chen to make sure he understands what we're talking about. Shang-Chen, do you understand the principle of detail balance?
Actually, no.
Okay, so the idea is the following. Okay, I'm going to just go because it's sort of what Saloni is doing. Basically, her system does not obey principle of detail balance. But the principle of detail balance is something that's equilibrium statistical mechanics that you studied so far is based on. Okay, let me just do a sketch here. Okay, so basically the idea is the following. Okay, so if you have a state A, okay, and then you have a state B, okay, they have different energy, but then the system can go back and forth. Then the population of A times the probability of A go to B is equal to the population of B times the probability of B to A. Okay. So if this is satisfied, it is said the system has reached the equilibrium. Why? Because the net flux going through here is 0. Okay. So which means this assumes that A doesn't become C or B doesn't become D and so forth. Okay. You can only go A and B. So what it means is with the A energy is here, EA is here, and the B the energy is here. Okay. Then what happens is, what it says is, then NA divided by MB, the population difference, the ratio of the two, then is equal to the ratio of the transition probability of PBA divided by PAB, okay, the transition probability, okay, PAB. So usually what happens is the system energy landscape looks like this. Okay. So basically what happens is you're either at A or at B, but they're separated by some energy barrier, okay? So then what happens is, then you can work it out. This will tell you that this is the e to the negative, the energy difference between the two divided by the thermal energy, okay? So what this is what you study in equilibrium statistical mechanics, that the ratio is determined by this, okay? This only tell you about what happens at the infinite time. In other words, you don't care about how long it takes for this guy to hop over, because you have the patience to wait for infinite time. This only tell you about the equilibrium configuration, the distribution. It does not tell you how fast you reach the equilibrium. Okay, so this is called the principle of detailed balance. So this description is well established in statistical mechanics. You have been tested on, right? Okay, but then there are systems that for some reason you drive the system out of this equilibrium, and then this whole language framework that developed by Boltzmann, or the giant of the past, don't work. Okay, in this case, then you have to figure out new ways to describe the physics. So Saloni solved one or two or three of these problems. I don't know how many. I know you have 3 papers, right? 2 papers, or how many papers do you have? I forgot. But anyway, you got your PhD, you solved some problems, and so basically this is a very cool thing. Okay, okay, so that's the framework that Shangchen, you need to keep in mind when we said equilibrium or non-equilibrium. You need to, in your head, you need to do all this math in your head. Okay.
Okay.
Mike, am I right, Mike?
Pretty much, yeah.
Okay, all right.
Yep. Well, because the systems, some of these out of equilibrium systems basically never come to equilibrium. They're sort of one-way systems, and that the time evolution is unidirectional. And the question we're asking is, if the system, take a system which has a number of possible stationary states, is there some mechanism that selects a unique stationary state, the stationary state which is characteristic of the system, rather than characteristic of the way that you tune things?
And
basically the only way that anybody has been able to approach this question is to simply say, okay, this system is described by some partial differential equations, and you try to solve these. And of course, the only way of solving these PDEs is numerically. Because the equation is just too complicated to solve analytically, at least too complicated for me anyway. And so the question is there, but of course, if the evolution is purely deterministic, in other words, no external noise, then the final state seems to depend on all sorts of things, like the initial state, the protocol you use for changing control parameters and stuff. But this all, there's a lot of literature on that sort of stuff. Just doesn't sound right. Somehow it sounds like, it just feels that in all that stuff, there's something not right. And so what Saloni and I tried to do was to say, okay, we have a toy partial differential equation, which describes pattern formation. It's very simple, but at least you can put it on a computer. And then we looked at the question of if we add some random noise to this partial differential equation, what is the effect of this random noise? And the effect seems to be that it actually selects a unique state. In other words, the state the system ultimately ends up in is independent of how you start the system off. And so therefore the unique state might be, characteristic of the system itself rather than depending on various protocols, experimental protocols you impose on the system. And so that really is the ultimate aim of the work. We haven't been able to prove.
Okay, but yeah. Mike, everything you said so far is very general, right? But I'm pretty sure Shanchen has no clue what you're talking about until Saloni show us the equation.
All right, then Saloni, why don't you write down the equation of motion we look at?
Okay. Yeah, I can just it's in my slides. Okay. So the toy model that we are looking at is called the stabilized Kuramoto-Shevchinski equation, and we are working in one dimension to keep things as simple as possible. So the equation looks like this. So if you just want to look at the deterministic version of the equation, then you have the partial time derivative of some field u equals this linear operator. So you have a control parameter which is represented by alpha, and then you have a second spatial derivative and fourth spatial derivative acting on the field. So this is the linear part, and in order to see the interesting behavior that we want to see and to saturate the growth of the field, you have to add this non-linear part, which is proportional to the square of the gradient of u. And so that is the deterministic equation. But because we are interested in fluctuations, we add to that a stochastic term. And we model the stochastic term as simply a normally distributed random variable which has zero mean and delta correlated in space and time. So here the quantity epsilon is describes how wide the distribution of this variable zeta is. So since we are taking zeta to be normally distributed, epsilon will simply be the variance of the distribution.
Represents the strength of the noise, if you wish.
Yeah. Okay, so this term here looks like so this is d dt u, right?
Yeah.
So this looks like a velocity of something, right?
Yeah.
Okay.
Yeah,
so I'm just trying to understand the symbolism form. Okay. Let's say if I only have.
If you write down the Fourier space, it's perhaps a little more, at least the linear parts, a little more obvious what's going on.
Mike, I have my way of understanding things. Okay.
All right.
Look, this. If I look at this things, this looks to me like a spring, right? So
yes and no.
Let's say
well,
I'm making this one viscous, right? Let's say I put a negative here. This looks like a viscous drag force, okay? And this looks like to me a restoring force, right? This looks like to me it looks like this. And with the liquid around.
Okay, yeah, I mean, if you like, yes.
Okay. And then, then plus square d square dx square. Okay.
But
Okay,
the dx squared term is destabilizing.
Yeah.
Yes. So what this means is it effectively makes this spring constant k to be dependent on not only the position, but also depends on the depends not only on u, okay, u, and it also depends on the du dx. Okay.
Yeah.
Yeah.
And in fact d square u dx. So basically it's a I see, it's a very unusual spring, a pendulum in the viscous media. Okay, I get it. Okay.
Right.
Okay.
I mean,
Okay.
yeah, if you just look at the linear part,
Okay.
there are, and you simply take the Fourier transform of everything, then there are some of the modes will decay to zero, but there's a band of modes because of the d by dx squared term, which will grow, which will simply grow with time. And those are if you like, linearly unstable modes. And basically what happens is that the nonlinear term, the du by dx squared term, that mixes all these unstable modes together and spits out at the end of the day a single mode.
I get it. Okay. Yeah, move on. I get it, Mike. Yeah.
The equation is nasty, but if you write down a few things and play with it for a bit, you will eventually convince yourself this is what happens.
Yeah, I can show what we mean by stable and unstable modes. So if we look at a deterministic equation, we can see that u equals 0 is one of the is a steady state of the deterministic problem, because if you just plug in u equals 0, and then since u is uniform in space, the gradient of that also vanishes. So you can prove that u equals 0 is a steady state of this equation. Now we want to see when this u equals 0 state becomes unstable, and in order to do that, we take a small periodic perturbation. So this has some wave number q, and then it grows in time with some rate sigma of q, and we substitute this in
hold on. Oh, can you go back? Okay, so hold on. So are you saying this is e to the sigma qt?
Yeah.
Okay, so this is a
So if sigma is positive, it means it's growing, and if sigma is negative, it means it's decay. That's all.
I understand. So if I rewrite this would be e to the iq x. So if I were to write as a I omega t, and then this omega would be negative I
omega is just sigma.
Yeah. Okay. So you see basically some imaginary mode. So some mode with a finite lifetime. Okay. Yes. Okay.
Yeah, so sigma can actually be real or complex, and so if sigma has some imaginary part, then you get something that oscillates in time.
Mm-hmm.
But we are only focusing on time independent states, and so for us sigma is going to be purely real.
Hold on.
So we don't want to look at the states which are oscillating in time.
Yes.
So for us, we are only
Oh, you
interested in,
you want to make sigma to zero to become zero. I see. I got it. Okay. Okay. So
uh,
this is a mechanical way of finding a stable. This is an ad hoc way of finding a time independent solution.
Sure, everything's ad hoc.
yeah,
Uh-huh.
yeah. So
Okay.
when you substitute this perturbation in the deterministic equation,
Mhm.
you can and you convert everything to Fourier space, you can show that the growth rate is given
Mhm.
as a function of q in this form. So this is
Mhm.
nothing but a dispersion relation like you do in solid state physics,
Yes.
right?
Yes. Yes.
Yeah. So so if you plot this relation in um, if you plot this relation on a graph, you end up with something that looks like this. And so this range of q for which sigma is positive
Mhm.
denotes the states, the periodic states which can grow as a function of time.
Mhm.
So in other words, for these values of q, our uniform
Mhm.
steady state u
Mhm.
equals 0 becomes
Mhm.
unstable, and the system goes into one of the states with uh, one of the states lying in this band.
I understand. I understand. So
Yeah,
everything here would decay exponentially, right?
yeah,
Yeah,
Okay.
yeah.
yeah. I mean,
So
though, yeah, all other modes are just called linearly stable because they decay back to zero.
Mhm.
hmm. So we can show with a little bit of algebra that sigma will be positive whenever alpha is less than alpha critical, which turns out to be 1/4, and whenever q squared lies in the range given by this inequality. So QC is known as the critical wave number, and it is simply the wave number for which sigma of Q is a maximum. So QC is this is this mode, and uh, and so the width of the uh, unstable band can be expressed in terms of QC
Mhm.
in this form. So q squared must lie between qc squared minus square root of alpha c minus alpha and qc squared plus square root of alpha c minus alpha. So it's just giving you a range of q's where the uniform state is unstable.
This is
And
for alpha is less than a quarter, of course.
yeah, yeah, yeah. So so now we can reformulate the question of selection in the following manner. So since we know that there is a continuous band of periodic states which which are unstable whenever alpha is less than a quarter, we want to find out what happens if we add a noise term to the equation. And in particular, we are interested in finding out if there is one particular wave number which becomes more probable than the others in the presence of noise.
Mhm.
So, and so in order to do that, what we do is we take the stochastic equation and we integrate it forward in time. And if the idea is that if you do that for a sufficiently long time, uh, you should be able to get the stationary probability distribution of the various wave numbers, right?
So this is you're going from a Langevin equation to a Fokker-Planck equation, right?
Not really. No, we always work in the Langevin formalism.
Then how do you get a probability out of this?
So you get
Oh.
a
on.
probability by integrating this equation for a very, very long time and then counting the number of times each periodic state is visited. And so
Well, that's a Fokker-Planck.
yeah.
That's
So
Like,
ultimately,
I mean, of course, the Langevin equation is completely equivalent to a Fokker-Planck equation. You just don't use Fokker-Planck formalism. That's all.
So for one sigma 1, you get this trajectory. For sigma 2, you get this trajectory. Get a third, you get this trajectory, right? You get a, and then what you do is you bin them, right? You bin them, right? For different. So that's exactly a Fokker-Planck.
Well, actually, what we actually do is we simply run it for a very long time in what looks like a stationary state. But of course, it's not completely stationary because of the noise. And we simply look at how long, for what fraction of time the system is in a particular periodicity. And that's how we calculate the probabilities.
yeah, so the stationary probability that we end up with when we simulate this in time is simply the stationary solution of the Fokker-Planck equation.
Okay.
Yeah.
But and of course, because we're all too dumb to do this thing analytically, we're forced to do things numerically. And of course, it's not, I mean, it's obviously a fairly simple, it looks like a fairly simple simulation, but we need to run it for a very, very long time.
Yes, but it's not trivial at all. So because you need to basically solve the equation for, this is a white noise, right? This is a white noise, right?
Yeah, Gaussian distributed, yes.
A Gaussian noise. Basically, so basically you need a, so this psi thing, this psi is basically something like this, right?
And we're making the assumption.
Right. Okay, so
that
basically,
the time average is equivalent to the disorder
Trajectory.
Average. Yeah, right, trajectory. So basically, what you do is you take each value, you run this equation numerically, you get the uxt, right? You get this uxt for this guy equal to say 0.01, okay? And then you do it again for 0.02, right?
Yeah. So at each time step, you have some different value of zeta.
Right. But if you take this psi to be 0.1, if you run the second time, you don't get exactly the same trajectory, do you?
No, it's a different trajectory every time.
But
average.
I thought this is deterministic, isn't it?
So
I'm sorry, what?
But this equation is deterministic.
yeah, this part is deterministic.
What I'm saying is, if I set this psi to be a
We choose
value,
them. No, but each time step, time and space point, we choose. We pick a value of noise chosen from a Gaussian distribution.
Yeah.
I see. Shangchen, I don't know whether you get this or not. Okay. So this simulation as a function of time, you do this integration of this equation, but every step of the time, every step, this T1, T2, every step of the time, you pick a random number from this distribution.
Yep.
Every time, okay. and
Yeah.
then you get a result. So you could run exactly the same run again the next time, but because
I mean,
every time,
in the sense you're talking about, it's deterministic.
yes, but
Yeah.
because every time you pick a number is different from the previous one because it's a random number.
Yes, yes.
So you question, you won't get the same result. Okay, I get it.
Right.
I
I
get
mean,
it.
if we were to, I mean, okay, for a given sequence of noise, of course it's a deterministic problem, because if we were to repeat the simulation with exactly the same set of noise parameters, we'd get the same result, of course.
Right. But the noise is different every time we pick. Yes, I understand. Yes.
Right.
Yeah.
Yeah.
And we assume that averaging over time, you know, in the stationary or the saturated regime, that doing a time average, you know, of just one trajectory is equivalent to averaging over noise. That's an assumption.
So basically the system is ergodic.
Yeah. I mean, we tried, I mean, in a second paper where Saloni looked at some different things, we actually had to do an averaging over different realizations of noise. And that was a very, very difficult computational business, because, you know, even averaging over, let's say, 200 different realizations of noise is a long simulation, and is not enough. You know, averaging over 200 realizations of noise is not enough averaging.
Got it.
So the only way of getting, well, the best way to get smooth results is to assume that a time average and a noise average are equivalent.
Okay.
Yeah.
So now the problem is clear, right? Now we know what exactly we want to do, and so before we actually start solving the problem, it's useful to get a sense of the properties of the deterministic equation. So since we are interested in the stationary periodic states, it's useful to look at what these states actually, how they actually look in position and in Fourier space. So here I'm showing just one example of a periodic steady state, which has some wave number q bar, and the really interesting things are visible once you convert this to Fourier space. And so it turns out that you can write this solution as the sum of the harmonics of Q. So L is some integer between, between minus infinity and plus infinity, and you can show that the only terms in this series which contribute are or rather you can show that the solution, the stationary solution will only contain the harmonics of the wave number q. So this will look like u tilde of L equals 1 times e to the iqx plus u tilde L equals 2 times e to the 2 iqx, and so on. So that is why in Fourier space you see these peaks at the first harmonic. So this is q equals q bar, and then this small peak is q equals 2 times q bar, and you will have a succession of these peaks, but the peaks will keep getting smaller and smaller as you go to higher and higher harmonics. And
Can I just interject one thing? One minor complication here is that a priori you don't know what the Q is. Right? I mean, you don't know a priori what the position of the first peak is. The peak at 0, that is an artifact.
Yeah, the peak at 0 simply means that, so if you look at the solution in position space, the 0 peak means that the average, if you were to take the spatial average of this solution, it would not be 0, but it would be some non-zero constant.
This looks to me, this guy looks like a plane wave, right?
Sorry, it looks like a what?
A plane
Yeah.
wave. A plane wave.
Oh, plane. You could call it that, yes.
Okay, so with a amplitude, that depends on time.
No, the point is it doesn't, because it's a stationary state.
But
Yeah,
what about the
so-
time here?
Yeah, so
Yeah,
this is not a stationary state. This is just a general solution as a function of space and time. But when you go to the stationary state, you can remove the time dependence.
Okay. Okay.
Yeah, so this is a dynamic solution, but we will be interested in the long time solution where everything becomes time independent.
Okay.
Okay, so for now, the important thing is to remember that the solutions of the deterministic equation will consist of these harmonics of the base wave number q bar, right? So now let's see what happens when you add noise to it. So I'm just going to quickly show my results, because again, there is a lot of previous literature, but that's not immediately necessary to know. So what we did was, like we mentioned earlier, is that we integrated the noisy SKS equation for very long times, and to do that, you have to discretize not only in time but also in space. So you define a spatial lattice of with n lattice points separated by some lattice spacing h, and then you convert you convert the SKS equation into Fourier space, and because you have a discrete lattice, your Fourier wave numbers will also be discrete. And so this is just like in quantum mechanics, where the wave functions have some discrete wave number, right? So if you impose periodic boundary conditions, you can show that the wave numbers can only be integer multiples of 2 pi over nh. So small n is some integer, right? So essentially what we are doing is, instead of solving the equation in position space, we will be solving for these u tildes, okay? And we will do this over some very long time interval, capital T. And so to find the stationary probabilities of each wave number, we will count the number of times each q is visited. So in other words, you have this function which is known as the indicator function, and at each time step, if the indicator function is or rather, if at each time step, if your system is in a state with wave number q, then the indicator function becomes 1 for that wave number q. And so the indicator function for a given wave number qn at a given time is 1 if the dominant wave number in the Fourier transform is equal to qn, and it is 0 otherwise. So essentially what you end up with is a histogram of the various cues, right? And so if you if you assume that the time interval t is long enough, you you should end up with stationary probability distribution, which you would get by solving the Fokker-Planck equation. Okay. Okay, so we want to know whether the stationary probability is peaked at a given wave number, and then that would be our selected wave number.
Can I give Shangchen a crash 2 minutes introduction of the Fokker-Planck equation?
Yes.
Shangchen, okay, so the Fokker-Planck equation that Saloni is referring to is this equation here. It's called the dp, the probability at a position x at a time t is equal to a constant, a diffusion constant d square p dx square, okay, and minus a velocity dp dx, okay. So what this guy comes from is the following, okay. The idea is the following. This is what called the Fokker-Planck equation. It's called also diffusion equation. So you can derive this equation very easily by discretizing the space. Let's say the step is A, and you call this step n. This is n minus 1. Okay, this is n plus 1 here. Okay, so you ask the probability. So you assume the probability you have, let's say at NA at say m tau time. So this is your x. Okay, this is x, and then this is your time t. Okay, ut. Okay, so your probability at position x at time t is equal to half of the probability when you were at on the left hand side n minus 1a at a previous time n minus 1 tau. Okay, you have the probability here. You have the probability going left, half going to the right, and then the same is true for the one on the right. Okay, so the idea is you're at this moment, at this time, you are composed of two half probabilities from the left and right. Okay, n plus 1. Okay, a, and at a previous time n minus 1 tau here. Okay. Okay, so
maybe it's plus 1. M plus 1 tau.
No, it's also minus 1 because it's from previous time. So both is from the previous time.
Okay.
Your current time is from your where you the physics is the following. We are the result of the past, not the result of the future. Okay, we're the result of the past. Okay. So if you subtract, okay, if you subtract on both sides, p, let's say n NA, the same place, but at m minus 1 tau. Okay, let's say if you subtract both sides by the same quantity here. Okay, m minus 1 tau. Okay. Okay, so what you do is, because you can break up this one into two halves, you can make this one 2 divided by 2 here. Okay. You can subtract this guy 2. So then what you do is you take one of this 1/2, combine it with this guy here. Take another 1/2, combined with this guy here. You will see that this is the derivatives twice, and here is the derivatives once. So by doing this, you immediately recover this guy here, and then immediately you recover this guy here, okay? And then so we can go over these details, but this is the idea about the Fokker-Planck equation, which is a very powerful equation in many contexts in physics. You must know it, okay? So we can go over these details later.
Yeah, I can send some useful references later.
Okay.
Yeah.
I mean, the important thing to remember is that you can either work the Langevin formulation or the Fokker-Planck formulation. They are equivalent.
Yes.
But it just depends on which is more convenient for whatever, you know, we use whichever formalism is more convenient.
Yeah, for discussion. Yeah,
In
for
the-
describing
in
the physics. Yes.
In the limit of, you know, the time interval going to zero,
Yeah.
and so on and so forth, everything becomes exactly equivalent.
So let me quickly show some results of this procedure. So we carried out this procedure for different values of alpha, and on the right I'm showing the stationary probability distributions obtained when alpha is equal to 0.2. And so what we have is on the y-axis the
I'm in
fraction
the
of
meeting
time.
right now.
Sorry.
Sorry, I'm talking to my wife, and I said it's okay. It's okay. She's offering me food, free food. I said thank you very much. It's lunchtime, so but it's okay. We can finish and then we have lunch.
Yeah, I can be very quick.
Okay. Okay.
We don't need to go over every single detail.
Okay.
So these are the stationary probability distributions for all the periodic states for a given value of alpha, and this wave number here is the critical wave number. But we see that the stationary probabilities are actually peaked about a wave number which is which is much less than QC, right? And we were able to show this for a range of noise strengths as long as the noise was greater than a threshold value. And the reason for that is if your noise is too small, your system will just get stuck in one periodic state and will not be able to escape and explore all the other states in the computational time available to you. So we always had to make sure that our epsilon was greater than the threshold epsilon min, and as long as we stayed in that in that noise regime, we found that the probability distributions were always peaked about a single wave number, which we call Q star. And you can write that in the in a discrete form as 2 pi times n star over capital N times H. And so this n star is going to be some integer, and and so the corresponding Q star will be your selected wave number. And you can and so we can say that this Q star is some property of the SKS equation, because Q star does not depend on what your initial condition is, and it also does not depend on the noise strength as long as this condition is satisfied. So in that sense, Q star is an intrinsic property of the SKS equation. And so you can do this procedure for various values of alpha, and then you find that as alpha decreases from 0.25, the selected wave number also decreases and becomes smaller and smaller with respect to QC. So the orange line is QC, and the blue, sorry, what?
No one asked question.
Okay, so the blue the blue dots are the Q star values that we found. And so you can see that as you go further from the critical value of alpha, the selected wave number goes further and further from the critical value. So now, so what we have now is we have the stationary probabilities, right? We know that at very long times, the probabilities will be peaked around some wave number Q star. But the next step is to find why that happens, because the stationary formalism will only tell you what the selected wave number is, but it won't tell you why that wave number is so special. And so in order to do that, we have to look at the dynamics of the system as well, instead of only looking at the stationary probabilities. And so to look at the dynamics, we now have to switch to a trajectory average, right? Because the long time average doesn't tell you anything about the dynamics. So we need to look at the trajectory average and see how the various modes evolve as a function of time. And so in short, what we did was we repeated the stochastic simulation for a large number of noise realizations, like Professor Kosterlitz mentioned in the beginning. So we averaged over some 200 noise realizations, and then we took the average over all of these trajectories, and that gives you the time evolution of each mode in terms of the structure function. So for each trajectory, you calculate the mod squared of u n tilde at each time step, and then you average over all the trajectories, and that gives you the time evolution of the structure function. And so once you do this, what you end up with is the time evolution for each value of n. And so you want to see which you want to determine for which values of n the structure function takes some non-zero value, and for which values it just decays to zero. Right?
May I ask a question here?
Yeah.
How do we know that this averaging is convergent? In other words, you said that you did some 200 time steps. What if you do like a 2000? Does the results change?
So it won't be 200 time steps, it will be 200 different trajectories. And so so what,
and each trajectory involves is a separate simulation.
yeah.
So this bit of the work is, to say the least, a little bit time consuming.
Yeah, and to address the question of convergence, what I did was to so I did an average over 200 trajectories, and then I did an average over say 250 or 300. And so if Sn approaches the same value at long times, then you can reasonably assume that the system has converged. And again, we will see that the exact value of the noise will be important, because if your noise is not large enough, then the initial conditions will determine the final value of Sn, because again the system will get stuck in one state, and so when you do the trajectory average, that need not be the same. That need not be the same if you increase the number of noise realizations. Okay. So we did this procedure, and what we ultimately found was that if you plot the structure function for different values of n, and you compare the evolution with and without noise. So in the top left and top right, I show how the structure function evolves when there is no external noise. So in other words, if you simply start with random initial conditions and you average over all the initial conditions and follow the time evolution of the structure function, you see that the structure function is maximum um, for some value of n, which is very close to the critical value, and the structure function corresponding to n star is negligible. So if your n star was equal to 209, then s of 209 is 0 at long times, which simply means that if you start from a huge basin of initial conditions, you are most likely to end up in a final state which is close to the critical state. And the noise selected wave number is very, very unlikely if you are if you are working with the deterministic system, right? But now if you repeat this whole procedure with some non-zero value of noise, what you see is effectively a flipping of the structure function dynamics. So the maximum value of the structure function in this noisy case is is obtained for n equals n star, which happens to be 209 for our alpha value. So our alpha is fixed at 0.2. So
Incidentally, the system size Saloni was using, I think it was 4,000,
yeah,
a chain of 4,000 sites, wasn't it?
yeah. And so in the noisy case, this 209 is the dominant wave number, and the critical wave number, which happens to be 225, is negligible. So the noise kind of reverses which wave number happens to be dominant at late times. Okay, so in the deterministic case, the critical wave number happens to be dominant at late times, but in the noisy case, the critical wave number becomes negligible, and the n star, which we first found from these time averages, becomes dominant. So this is the n star that we found from the time average, and that same n star is now dominant in the trajectory average as well, right? And so you can show that the reason for this flipping is that the nonlinear terms in our equation of motion are modified by the presence of noise. So we go back to our original equation. If we go back to our original equation, you can show that the linear terms are unchanged by the presence of noise, but the nonlinear terms are modified in such a way that that the critical wave number becomes highly damped and the selected wave number becomes amplified. So that is a whole separate calculation which we don't need to go over right now. But the end result is that you can now understand why the selected wave number is so different from the critical wave number. That's the whole point of this entire exercise. And then finally we again repeated this procedure for different values of alpha, and we were able to show that if the noise is large enough, you can if the noise is large enough, the dominant wave number found through the structure function dynamics is the same as the selected wave number found from the long time averaging. So yeah, that again shows that time averaging is equivalent to trajectory averaging, but in order to see that, you have to have the noise strength to be larger than a certain value. If the noise strength is not large enough, then it takes you a very, very long time for the structure function dynamics to saturate. So in that case, you can't you can't prove anything because you don't have the computational resources to do such a long integration. So so for practical reasons, we have to keep the noise strength greater than epsilon min. But this is the essence of what I did during my PhD. So first I showed that at very long times, there is one wave number which is most probable. And then in the second part, I showed why that particular wave number is more probable. And the way to do that is to focus on the dynamics instead of just looking at the stationary probabilities. So that's what we have done.
Okay, all right, thank you.
Saloni, from a practical point of view, I think it might be an idea if you talked a little bit about the algorithm you use to do the computation, because that was quite a breakthrough, and without being able to figure out this method of using enormous time steps, we wouldn't be able to do this.
You need to share the code with us, okay?
Yeah, I will share the code, and because we are running a bit late, I can just show you which paper I used as a reference to write that code.
Okay.
Let's see. Yeah, it is this paper by Chen and Shen, and so the concept behind the algorithm is explained very well in this paper, and the main idea is that if you have a nonlinear partial differential equation, so here eta is some field that you want to solve for. In our case, we are calling it U. So f of n is some nonlinear term, and then you have a del squared of n. You can what you essentially do is you use explicit time integration to solve the linear term, you use implicit time integration to solve the linear term, but explicit time integration to do the nonlinear term. So so what is explicit and implicit? So explicit time integration means when you use the value of the field at the previous time step to calculate the value at the next time step. But when you do an implicit integration, what you're doing is you're using the value of so let's see if there's a clear way for me to so your explicit time integration means that you are solving for the value of eta at n+1 in terms of the value of eta at time step n. Okay, so this is purely explicit. But if you want to do an implicit integration, that involves how does he describe that? So the nonlinear term f of eta should be evaluated by using hold on, where does he actually explain? So the semi-implicit scheme, this is the one that I have used in my code. And so instead of using the explicit scheme where you have the value at n+1 in terms of the value at n, you can write a modified equation in which you can write the value at n+1 in terms of the value at n and the value at n+1. So you're basically taking an average of the value of the field at time tn and time tn plus 1. And then you're writing the new field in terms of that average. So so the calculation to get this is pretty straightforward, and it is explained in this paper. And this is the sort of algorithm that I've used. And the advantage of this algorithm is that you can take delta t to be pretty big, because in the problem with the explicit integration is that delta t has to be some very small number which is proportional to delta x squared or delta x to the fourth. But in this semi-implicit formalism, there is no such restriction, and so you can use much larger values of delta t, and hence your simulation becomes much faster. So I can send you this paper and I can send you my code, and then if there are any more questions, I can talk to Shancheng directly.
Yes.
Yeah, that would be a good idea. Thank you.
Yeah. So Nani, when are you leaving Providence?
I'm leaving on the 25th of May.
25th of May. So you have about a month still here. Okay.
Yeah.
Okay. So then that's great. Shangchen, so why don't you first get the code and the reference from Saloni, and then make sure you understand in terms of the technical things, how to implement. I would suggest that you take the code from Saloni and then run it once on your computer, okay? And if your computer is too slow, then I can let you use the computer in my lab. My lab has a workstation that has a pretty fast processor that you can run on, okay? And then so make sure you know how to run the code before she leaves. So obviously it will take you some time to appreciate what she has done, but that's going to take a much longer time. Okay, first you need to know, why don't you do this? I suggest you just run a particular result of her code that make sure you can reproduce what she got on her thesis. Okay, so Nani, can you give a copy of your thesis to Shangchen?
Yeah, I can do that.
Okay.
Now my code is written in Python.
Yes.
So are you familiar with Python?
I can learn it, and
Yeah,
I'm
but
not.
You know C, right?
Yes.
Okay. If you know C, Python you will know in 1 hour. Okay. Even
Yeah.
I know how to use Python, so then that shouldn't be not a problem. Yeah.
Yeah, or otherwise, once you understand what the code is, you can simply rewrite it in C.
Yes.
Straightforward.
Yeah. Okay. So Sonali, I because Zoom would delete all our Zoom recordings in I don't know how very quickly, and they have deleted many of my class videos. So what I want is I'm going to put it on the YouTube. Do you mind I put it on the YouTube? Is there anything that is unpublished in this video that you would object?
No,
Because
it's all published.
okay, so I'm going to put it on the YouTube that if you want to watch, you can watch it too. Okay. All right.
Okay.
Okay. Okay. Okay. That's great. Thank you very much.
Yeah.
Shangchen,
Well, but actually, you know, the algorithm is essentially written down in one of Saloni's papers, and you know,
Yeah, the derivation. So what I'll do is I'll send you both my papers, my thesis, and the code. I will also, I think it will be useful for me to put some comments in my code just so that he can understand what each step of the code is doing.
yeah, that would be great.
fabulous. That would be really good. Thank you very much.
Yeah, because
really good. Yeah.
the code is like, I'm so familiar with it that I just add things to it, and I don't need to add comments because I know what everything's doing.
Yeah, this is the trouble with trying to read something written by an expert, is because the expert knows this stuff so well that the expert forgets really how dumb the readers are.
Okay, so Sonali, let me make it a promise. So if Shangchen produce anything that's publishable, we will put you as a co-author, okay? If you're helping him along the way, okay?
Okay.
All right, Shangchen, do you agree?
Yes, I agree.
Okay, all right, okay. So let's do that. Yeah, okay, so then we'll communicate by email, okay? It's lunchtime. Thank you
Yeah.
very much. Let's go have lunch.
Bye, Professor.
Bye.
Okay,
Right.
bye. Bye.
Yeah.
Bye.
Okay.
Bye,
I
Mike.
mean,
Bye, Mike.
yeah,
Bye,
bye,
Mike.
Sean. Aren't we
Bye.
supposed to go have lunch tomorrow or something?
Mike, I have my second shot on Friday, so I'm not going to lunch until I have a second shot.
Okay, that's fine.
Okay.
Right. But then you have to wait for a week or two after the second shot for
Yes,
be fully.
May 15th is the target date for us to go to Japan lunch. Okay.
When you're back to your usual risk-taking self.
Right.
Right.
Okay.
Okay.
Okay. Bye.
Yeah. Thanks a million, Saloni, because that's very useful
Right.
communication.